Yes.
Okay, we are ready, sir.
Okay.
Okay, dear participants, I welcome you all to the opening of International Webinar on Nuclear Shell Model, organized by Department of Physics at Akal University, Talwandi Sabong. I am delighted to introduce our distinguished guest speaker for this webinar, Professor Peter van Isacker, an eminent researcher at GANIL. GANIL is a large heavy ion accelerator facility in Sion, France. Professor Isaac's contribution to theoretical nuclear physics have significant impact on the understanding of nuclear structure and dynamics. And we are privileged to have him as our guest speaker. Professor Isaac's curriculum vitae is a perfect example of his exceptional dedication and hard work in the field of nuclear physics. With 2 PhDs from University of Ghent, Belgium, and an extensive publication record comprising books, monographs, review articles, and over 289 scientific articles in referred journals such as Nature Physics, Physical Review Letters, Physical Letter B, Physical Review C, and many more. The number of citations according to his CV is more than 7,500 and H-index is about 40. But as per ResearchGate profile, the citation are more than 8,600 and H-index of 47. He has delivered 83 seminars, 33 summer school lectures, and 152 invited talks. Professor Isacker's research contribution span a wide range of topics, from extension of supersymmetry in nuclear structure to the role of isospin symmetry in collective nuclear structures. He has also guided 10 PhD students. In addition to outstanding research accomplishments, Professor Isacker is also a great teacher and taught several courses on nuclear physics and general theory of relativity. I encourage all participants to actively engage in discussion and ask questions and grab this opportunity to learn from Professor Isacker's knowledge and experience. Once again, I extend my regards to Professor von Isacker and welcome all participants. May this webinar impart a useful contribution in enriching our understanding of nuclear shell model and its implication for fundamental physics. Over to you, sir.
So, good afternoon. So thank you very much for the invitation. Thank you also for the introduction. You were too kind. So one thing I should say, if there's something you cannot understand or if it's not clear, you should ask me, because I'm just talking to my screen and I don't know to what extent you will be able to follow. Okay, so what I wanted to do in this lecture is to give you an introduction to the nuclear shell model. So what I first would like to do is to give you some of a little bit of an overview of nuclear model. So where does the nuclear shell model fits into the overall picture of approaches to solve the nuclear many-body problem? And so this is a little arbitrary, but I sort of, if you given a list of possible approaches to solve the nuclear many-body problem, and the most microscopic, the most fundamental approach, which is these days very popular, is what is called ab initio methods. So ab initio, that means methods that go from the start, and these are completely microscopic methods. And so the aim is to describe nuclei starting from the bare nucleon-nucleon interactions. So that can be two-body interactions, but possibly also three-body interactions. So that is now a very popular approach. And this is actually, it has a connection with the nuclear shell model. The only sort of additional step in this method is that you will not fit your interaction, but you will deduce your interaction from fundamental methods and in particular from QCD. Now, at the moment, this is not possible yet. And so people still have to put in coupling constants, so parameters, in order to do such calculations. And the reason is because QCD at low energy is a very difficult business. So that's it is not possible yet to do QCD calculations at low energy, the energies that we need in nuclear physics. So that is a completely microscopic. The nuclear shell model is a little bit less microscopic in the sense that you assume a nuclear average potential and then residual interaction between the nucleus. And I will come back to this to explain you in detail what that means. Right? Then we have what I would call mean field methods, and that is where you have a global parameterization. So you probably have heard things like the GANIL force or the Skirm interaction. So these are interactions or potentials that you propose for all nuclei, and with that potential you try to describe the overall picture of nuclei. And then last, which I think is still, this is a useful approach, these are phenomenological models. So these are models that you will not apply across the nuclear chart, but you will go and try to describe specific nuclei or specific properties with a local parameterization. And also, one of the characteristics of phenomenological models is that you usually have some kind of an intuitive picture of what is happening with the nucleus, which if you do completely microscopic calculations, this might be lacking, because then you have just a numerical procedure to solve your nuclear many-body problem, which is very complicated. And so intuitive insight sometimes is lacking. Okay, so if I want you to talk about the nuclear shell model, I should start with the most basic version of it. And the most basic version is called the independent particle shell model. So what is the assumption? The assumption is that you have individual neutrons and protons. They do not interact with each other, but they're placed in a mean field potential. And again, I will make this more technically precise in the coming slides. And so we have, and that is happened in the middle of the last century, people started to realize that, of course, they were familiar with shell structure of atoms, but they started to realize that a similar shell structure is happening in nuclei. And so what came about was that it was realized that there are what is called magic numbers, 2, 8, 20, 28, 50, 82, and 126. And at those numbers of nucleons, either neutrons or protons, your nucleus obtains an increased stability. Okay, and so that came out of the crucial ingredient actually for this to happen. These specific magic numbers, the crucial ingredient is the spin-orbit interaction, and that is actually that was a remark by Fermi in the 1940s, who said, well, maybe there is some spin-orbit interaction, and that might modify the shell structure of your nuclei. And so I should remind you that this shell model was then awarded the Nobel Prize in 1963. So Guppertmeyer and Jensen for their discoveries concerning shell structure, but also shared with Wigner for his contributions to the theory of the atomic nucleus and elementary particles. Okay, so what are the sort of the global characteristics of the nuclear shell model? So first of all, there is a mean field potential. And then again, I will explain that a little bit more in detail later on. And there is a residual interaction between some of the nucleus. So if you do independent particle shell model, then you only have a mean field potential and you neglect the residual interaction. So this is a difficult problem. This, I mean, one should realize what are the difficulties? First of all, unlike, for instance, in atoms, where you have electrons and you know very well the Coulomb interaction between the electrons, this is not the case in nuclei. So nuclear interactions, they're very complicated, and essentially that is due to the fact that the nucleons are not elementary particles. They're made up of 3 quarks. So you have to derive these nucleon interactions from QCD, and that is a complicated business. So the interaction is very complicated, unlike the Coulomb interaction between the electrons, for instance. That is one part of the problem. Another part of the problem is that you have to deal with very large Hilbert spaces. So if you, I mean, typically a nucleus will contain something like 100 nucleons. So that's a large number to treat explicitly. And so if you want to do that explicitly, you have large Hilbert spaces, and dimensions are very large, and so you have to do large matrix diagonalization. So what are the issues of current interest? Well, so probably you know that in nuclear physics, in nuclear structure, there is a great interest in what is called exotic nuclei. So these are nuclei which are removed from the valley of stability. And let's say since about 20 years, it has become clear that those magic numbers that I showed here on this transparency, these are valid for nuclei that are close to the line of stability, but they might not necessarily be valid for nuclei that are exotic, so that are very deficient in neutrons or very rich in neutrons. So the changing shell structure, that is an important domain of research in nuclear structure at the moment. And the other point is three-body forces. I will not go into that in these lectures, but this is, again, this has to do with the fact that you're dealing with non-elementary particles. The nucleons are not elementary. And then three-body forces might arise. Another topic of current interest is continuum effects, precisely because you go now to exotic nuclei, so which are very rich in protons or very rich in neutrons. These nucleons, the last nucleons in your nucleus, let's say, these are very weakly bound. And so it's easy to pull out a neutron or a proton from an exotic nucleus. And that gives rise to what is called continuum effects or open quantum systems in the weakly bound systems. So these are, they display all kinds of specific effects that are of interest and that are being studied at the moment. So, a few words of warning, because the shell model is a model. That is something you should not forget. And it is a certain way of modeling the wave functions. And sometimes if I discuss with my colleagues that do shell model calculations, they sort of have the tendency to believe too much in the truth of their wave functions. And I think one should keep in mind it's a particular procedure to solve the nuclear many-body problem. And so these wave functions, they are not the true eigenfunctions of the nuclear Hamiltonian. The nuclear Hamiltonian is too complicated. I'm not sure whether we will ever get to the true eigenfunctions of the nuclear Hamiltonian. The shell model is a valid way of approximating these eigenfunctions, but it's not the final word. And then the other thing which I like, this is a quote from Wigner. Wigner was very active in symmetry principles applied to various physical systems, quantum systems in particular. And so one thing which is typical of current nuclear physics is that it's a numerical procedure. Nuclear physicists are heavy users of computing. And so this is a quote from Wigner. It's nice to know that the computer understands the problem, but I would like to understand it too. And that is saying something about it's always nice if you do a numerical calculation, then construct some kind of an approximate model of an approximate intuitive understanding of the problem you're dealing with. And I think that is something one should not forget. Okay, one thing I would like to show also is, this is an illustration why this is a complicated problem. You see, this is the nucleus lead-199. So it's a semi-magic nucleus, so it has 82 protons, so that is a closed shell for the protons, and then 117 neutrons. So it's not so far removed from lead-208, which is a doubly magic nucleus. So you would think, this must be a simple nucleus. Well, it's not. It's not at all a simple nucleus. You see the complexity of this nucleus with sort of single particle excitations at low energy, which are come out of the nuclear shell model. And then at some higher energy, you see these regular structures that appear, bands that appear. And so nuclear physics or nuclei are characterized by this sort of these dual properties, single particle properties and collective properties, band structures and strong E2 transitions. So, and any theory should try to deal with those two aspects in a satisfactory way, and that is a very difficult thing. In the shell model, you can do it to some extent, but for instance, these bands here, to explain these bands in a completely microscopic way, at the moment, this is not yet feasible. Although this, in principle, should be a fairly simple nucleus. After all, it's a semi-magic nucleus. And then you see, this is a typical example of an open shell nucleus. So here, both the neutrons and the protons are not at closed shells, removed from closed shells. And then you see, this is the experimental spectrum of this nucleus, erbium-168. You see all these regularities. And so one should try to explain the regularities of these nuclei. And that, again, in a completely microscopic way, that is a difficult problems. It's even worse. I mean, this is erbium-166, I believe. And so you see all these band structure. I mean, the complete description of these bands is at the moment outside our capability. We cannot do that. we can sort of construct phenomenological models to describe them, but microscopically, this is not possible at the moment. Okay, so let me now give you a little bit more technical background on the basics of the nuclear shell model. So first of all, what I should say is that this is the approach is non-relativistic, so it's based on the Schrödinger equation, not on the Dirac equation. And so your nuclear Hamiltonian, what does it contain? Well, it contains a kinetic energy term, so this is p squared divided by twice the mass. Okay, and then summed over all the particles in your nucleus. So A is traditionally the way the number of particles is the mass number of your nucleus. And then, then you have an interaction between the nucleons. And here is this interaction. So I've taken here, for simplicity, only a two-body interaction. So a two-body interaction, that means it depends on the nucleons, on the coordinates of two nucleons, right? Nucleon K and nucleon L in this case. And so what is the basic assumption of the nuclear shell model is that you add a one-body potential to the kinetic energy and that you subtract it again. So you haven't done anything, right? But then you say, well, in the nomenclature to do this is called the mean field, right? So it is a kinetic energy term plus a potential, a one-body potential. And this is called the residual interaction. And so in the independent particle assumption that I was discussing in the second slide here, what you assume? You assume that the residual interaction can be neglected. So that is a very strong assumption, which is not at all exactly valid, but it's some approximation in order to get a first idea of what is the structure of your nucleus, right? And so you choose a mean field potential here, this V. You choose it optimally in such a way that you can neglect the residual interaction. It should be stated that the residual interaction is a complicated interaction, because you see it's a mixture of a two-body interaction and then a one-body potential. So this is equivalent to saying that the residual interaction, it's an interaction that depends on the environment, right? And the environment is sort of simulated by this potential, this one-body potential. Now, if you make the independent particle assumption, so you neglect the residual interaction, then you have this Hamiltonian. This is called the independent particle Hamiltonian. And that actually you can solve rather easily. So instead of the very complicated many-body problem with the two-body interaction, the independent particle Hamiltonian can be solved easily. This is an outline of how to do that, right? You can look at the solution for one particle. So this is kinetic energy and then the potential. This is a potential well where your particle is moving. So that's a standard Schrödinger equation for one particle, and that can be solved in most cases numerically, but it's fairly standard procedure to solve it numerically. In some cases, as I will discuss later, you can choose a potential such that you have an analytic solution of your Schrödinger equation for one particle. And once you have done a one-particle solution, you more or less have done the problem for many particles, but because for many particles, your solution is just the product. So here you have many particles. So you have 1 to 8 particles, right? And you can write the solution of the many particle problem for independent particle Hamiltonian just as a product of the solutions for the one particle. Okay, so this is written here. So you have the independent particle Hamiltonian. This is your wave function in A particles. And then, for instance, the energy is just the sum of the energies of the A particles of your one particle solution. This mathematically is a solution. Physically, it's not a solution because of the Pauli principle. So we are dealing with the system of fermions. So your wave function must be antisymmetric if you interchange two fermions, right? This wave function is not antisymmetric. So the way to do that is to make a Slater determinant, right? So this is the genuine physical solution of your independent particle problem, right? For instance, for two particles, here it is written, right? You have this, and then you have two configurations with particle 1 in one configuration, particle 2 in the other configuration, and then here the switched contribution where particle 2 is in the first configuration and particle 1 in the second one. And so this guarantees that your wave function is antisymmetric if you interchange particle 1 with particle 2. Yeah, I should say here that I've dealt here with the spatial coordinates of your particles. If you want to do the full problem, of course, you have to worry about the spin coordinate of your particle. That should be included. And also the isospin coordinate. I mean, whether you're dealing with a neutron or with a proton. Okay, so this is the solution of your independent particle shell model. Now, the problem is, of course, how to choose your potential here, right? This mean field potential. What is the best way to choose that? It's never going to be an exact solution of the many particle problem, but one can say, or I can ask, what is the best way to choose this potential? And that is known as the Hartree-Fock approximation. And so basically what you try to do, you take the Hamiltonian, the full Hamiltonian, and you minimize this expectation value of the Hamiltonian, I mean, between normalized wave functions. So these wave functions here, if you recall, these are Slater determinants. So they are antisymmetric, right? And so they're written in terms of those single particle solutions of your problem Schrödinger equation for one particle. So that will, of course, depend on the potential. And so the procedure is to choose a certain potential, calculate this expectation value, and then vary the potential or vary the single particle wave function in order to minimize the expectation value of H in a Slater determinant. And that is known as the Hartree-Fock approximation. Okay, this I will not discuss any further. What interests me more is what I would call, I mean, following a book by Rossum on the theory of the nuclear shell model, poor man's Hartree-Fock. And so you're not going to look at the most general potential that satisfies this Hartree-Fock equation, but you're looking for an analytically solvable potential. And the best one, in the case of nuclei, is to put, so this is the kinetic energy, but then to put here a harmonic oscillator. And then the important thing is that this harmonic oscillator, it's not sufficient in order to explain the magic numbers. And so what is crucial for explaining the magic numbers is the spin-orbit interaction and the orbit-orbit interaction, right? And so with this, you sort of get a reasonable approximation to a more realistic mean field potential. Okay, so what does it, this can be solved because this is a harmonic oscillator. So the harmonic oscillator wave functions, they're known in terms of Laguerre polynomials. And so this is the solution, the energy eigenvalues of the harmonic oscillator. And so, yeah, let me go a little bit through that because this is something that always comes back. So this is the contribution of the harmonic oscillator potential. So H bar omega, then you have N, which is the oscillator quantum number, and then 3/2 because you have the 0-point motion in 3 dimensions. And so this N, the oscillator quantum number, is equal to 2N plus L, where N is the radial quantum number. So this means the number of nodes of your wave function, and L is the orbital quantum number, right? So this is the angular momentum of your particle as it moves around in your mean field potential. And then J, of course, is the total angular momentum, because we should not forget that the nucleons have spin 1/2. So you have to couple, in order to get the total angular momentum, you have to couple the orbital angular momentum with the spin 1/2 of the nucleon. So this is the picture that comes out, right? This is an important picture. So here you have the levels that you would obtain for a harmonic oscillator. So 1S, sometimes the convention is 0S. You start counting from 0 or from 1, that depends on the convention. 1p, so S means L equals 0, orbital angular momentum 0, 1p, that means orbital angular momentum is 1. And then the next harmonic oscillator shell is SD, right? So this is N equals 2, capital N, this capital N here equals 2. And then you can have N equals 0, L equals 2, so that would be a T state, or N equals 1, L equals 0, that would be an S state, the second S state, and so on. So it goes on, PF shell, SDG shell. So for a harmonic oscillator, so all these levels here, which are characterized by the brackets, these levels are degenerate in energy. The degeneracy is lifted by the orbit-orbit, this term here, the orbit-orbit term lifts the degeneracy. Okay, and so you see that 2S is no longer degenerate with 1D, 1F is no longer degenerate with 2P, and so on. Okay, and then one step further, and that's very important, you have this spin-orbit interaction. So if you have a D level, so your spin, so D means L equals 2, so then you can couple to D3/2, to 3/2, or to 5/2. And so these two levels, they're split in energy by the spin-orbit interaction, right? And that becomes more and more important if you go higher in the harmonic oscillator. And so the feature is that your F7/2 is somewhat separated from the other levels in the PF shell. And so it becomes a shell by itself. Same thing here, the G9/2, it migrates to the shell below. So your shell structure is not any longer the harmonic oscillator. it's a modified harmonic oscillator, the modification coming from the spin-orbit interaction mainly. Okay. Then there are questions why orbit-orbit term. Yeah, that is more detailed. Basically, it's because you're dealing with a harmonic oscillator, and this harmonic oscillator is some approximation to a more realistic mean field potential. And as a consequence, you can simulate the difference between the two by taking an orbit-orbit term. Okay, I will not go more in details about this. Why a spin-orbit term? That is a more difficult question. So this has a relativistic origin. It comes from the Dirac equation. And so from, in addition, I mean, there should be some radial dependence of the spin-orbit term, which I didn't put here. Right here, I just have a constant, but that's not quite the case. It's some function of the distance from the center of the nucleus. And so it turns out that your spin-orbit term is important at the surface. Right? And so that has been some matter of debate over the years. How does the spin-orbit interaction changes with exoticity? Because if you're going to exotic nuclei, your potential is, your surface is more diffuse, and so there are some arguments to say that the spin-orbit interaction is less important, but that is still an open question. Okay, so this sort of ends the more formal introduction to the shell model. So now I would like to show some pictures and that go back to the data. And so the question that one has to ask, I mean, what is the evidence for shell structure in nuclei? And so here I've listed some features, right? And I will discuss in particular nucleon separation energies and nuclear masses, because I think that is sort of the most telling characteristic in order to show evidence for nuclear shell structure. And I will also show some example. The 2+ energy, excitation energy, is also some kind of a feature of nuclear shell structure. So let me start with nucleon separation energies. So this is a picture from atomic physics, right? So you see these peaks and then these sudden decreases in the ionization energy. So that means the energy you require in order to ionize a particular atom. And you see there is a structure, right? And this structure actually is indicative of the shell structure in atoms. So can we have a similar picture in nuclei? The answer is yes. Not so clear, but you see here, this is neutron separation energy. So this is the energy. You have a nucleus, so you want to pull out a neutron. So you need a certain amount of energy to pull out that neutron. And so this amount of energy, this Sn, as it is usually called, is plotted here. This is an old picture. It comes from a book by Borre Mottelson. So it's a very old picture. But you see, well, to some extent, you see that there is something going on at n equals 126 and n equals 82. It becomes much less clear if you go to lower masses. And one of the problems of this kind of plotting is that, I mean, here you sort of, you mix two kind of nuclei. You can pull out a neutron from an odd mass nucleus, or you can pull it out of an even mass nucleus, and that makes a lot of difference. And so that is why this picture is a little confusing. So it's much clearer if you look at two neutron separation. So that means how many, what is the amount of energy I need in order to pull out two neutrons. And here it is very clear. You see, for instance, at 50, so there is a steady decrease in this neutron separation energy that you can understand, because so the lines are all isotopes. So these germanium, arsenic, and so on. So the connection is between isotopes. And so you change the number of neutrons. And as you increase the number of neutrons, of course, it becomes more and more simple in order to extract a neutron, because the neutrons are more and more loosely bound if you increase the number of neutrons. And you see that this effect is especially important at, in this case, the magic number of 50. So you have a smooth behavior up to 50, and then suddenly the neutron energy decreases steeply. Why? Because your neutrons beyond n equals 50, they are more loosely bound. So the stability occurs for n equals 50, and so beyond n equals 50, there is less stability from cell structure. You see also that there are things that are happening here. So this is not related to a closed to a shell structure, right? This has to do with deformation. So this feature that happens around n equals 58, that has to do with deformation. So that has nothing to do with shell structure, right? Because your nuclei can also acquire additional binding energy by deforming. And so there is an effect of the deformation on the neutron or the two neutron separation. So this is another picture for n equals 82. It's more or less the same story. And then you see also there is some question of deformation energy if you go to open shell nuclei. And the same thing happens for protons. Okay, now maybe the best way to show, to illustrate shell structure in nuclei is by using the liquid drop mass formula. Now, in the liquid drop mass formula, there is nothing about shells. And it is just, as the name says, it is assuming that your nucleus is a liquid drop of dense quantum matter. Okay, and then there is this old formula which goes back to Isacker and later, right? So this is almost 1 century old, and so you see the binding energy of the nucleus. So the binding energy is the energy that you need in order to pull apart completely the atomic nucleus. And so this binding energy is a simple function of A, the number of particles, so the mass number, and then Z, which is the number of protons, and N, which is the number of neutrons. And you see there are different terms here. So there is this volume term. Clearly, I mean, the binding energy increases if the nucleus increases. Right? There is a surface term, nucleons, they don't like to be at the surface of the nucleus. So there is some decrease in the binding energy for all the nucleons that are at the surface. Then, of course, there is Coulomb interaction, which is repulsive between the protons. And then there is some symmetry. So this is a symmetry contribution. Actually, your nucleons, they like, this is the term where the nucleons like to be equally numbered, right? Whereas here, this term, Coulomb term, it likes to avoid protons because protons have a repulsive. And then this is the most basic interaction between the nucleons, which is the parent interaction. So if you do that, you have a simple model to describe binding energy. So these are the binding energies, and all. I'm sorry, it's an old. So these are the masses of nucleons of nuclei of atomic nuclei, which go back 20 years. And so this is your mass surface, right? I start with oxygen 16, so which has a binding energy of 128 MeV. And then I go to the heaviest nucleus here, right? Which I forgot which it was. But then you have something of the order, a binding energy of the order of 2 GeV. And you see, this is a very smooth surface, right? So you increase the binding energy very smoothly. But now what you can do is to subtract from this the liquid drop formula, mass formula. So remember, the liquid drop mass formula doesn't know anything about shell structure. So if you do that, you see very clearly now the shell structure that arises for the nucleus, at least for 50, for 82, and 26. A bit more complicated for the lower, for the lighter nuclei, but clearly you see 50, 82, 126. This is the same thing with later, I'm not going to discuss that in detail. So that's a later, so this is a mass compilation of about 12 years ago. And so you still, I mean, you have more nuclei, but still the same picture arises. Right? So you can do a little bit better and then look at modified liquid drop formula. And you add a Wigner term, which is this here, and then you, some shell correction. So let's say some phenomenological way of including shell corrections. And you see, if you do that, previously your RMS deviation was about 3 MeV. So that means on average your binding energy is 3 MeV off, right? And this is, remember that these are several thousand, 2000 MeV for the heaviest nuclei, right? So 3 MeV is a very respectable deviation. And you see, if you do then these shell corrections, these phenomenological shell corrections, where you count the number of valence nucleons starting from shell closures, then your RMS deviation is reduced to about 1 MeV. Right? The same picture now. So you have, that is the picture that I showed when we do this liquid drop subtraction. And so now you do your corrections here, your shell corrections, phenomenological shell corrections, and so then you reduce further your deviation. But still, so there's still, and then you see also for the lighter nuclei, these deviations can be quite important. And so that is indicative of the fact that the shell structure of your lighter nuclei is more complicated. And so you have the arising of new shells. For instance, shell number, magic number 16 is something that sometimes appear, or magic number 40, which is, you see a little bit here, right? This blue patch. This blue patch here is indicative, and so that means that you see for lighter nuclei, people have studied more exotic nuclei. They went closer to the drip lines, and so that means that there are some important deviations of from the classical magic numbers, and that shows up in this kind of picture. Okay, so this is the same thing, but then for mass, for the mass compilation of 2012. It's essentially the same picture. Okay, another feature of cell structure is very easily, if you look at the energy of the first excited 2+, and you see very clearly that this, for instance, well, I mean, we have to know the color code, but the color code, so some special features are happening for the magic numbers as we know them, right? 82, 126. And so these are characterized by specifically very high 2+ energies. And so that is just a consequence of the fact that it's difficult to excite your nucleus because it's rather stable. And so the first excited state is positioned at a high energy. And actually, if you look at these nuclei, like lead-208, here this red point, right, 82 for the protons and 126 for the neutrons, lead-208. So the first excited state is not a 2+, it's a 3-. So it's a completely different feature. And so that is typically valid for doubly magic nuclei. Okay, let me now say a few more things about, because what I discussed so far was the simple shell model, right, where the residual interaction was not taken into account. So of course, people who do shell model calculations, they're not satisfied with this. And so nowadays, a shell model calculations, that means you take the mean field potential, so you take kinetic energy and then this mean field potential, and you add to that a residual interaction. And then the question is how to describe this residual interaction, right? So a bit of nomenclature, a bit of, so valence nucleus, because you see, you have, if you want to describe a nucleus like lead-208, in principle, you should have 208 particles. That is beyond, at the moment, beyond the scope of most calculations. And so what people, there is a question. Shall we ask the question now or after the, hello? There is a question, I see.
Actually, I want to ask a question about 2+ state. How do we know that the 2+ state arise from a collective excitation or a single particle excitation?
Oh, the 2+.
Yes.
Yes. Oh, I mean, that is a difficult question, actually. That is not always so obvious. I will show some examples of nuclei where the 2+ is a 2-nucleon excitation, right? And that typically it happens if you have a semi-magic nucleus. So if you have a closed shell for the neutrons or for the protons, and an open shell for the other ones. Okay. Then in most cases, your 2 plus, it will be either some pure single particle excitation, or maybe some linear combination of the orbitals available for the neutrons or for the protons. If you go to an open shell nucleus, so where you have neutrons and protons active at the same time, then usually your 2 plus will be a collective excitation. And that is much harder to describe in the shell one. I will come, if I have the time, a little bit at the end, how to do that in the shell one. So it's not a straightforward question, and it depends on, it has to do with this dual properties of nuclei, both single particle and collective, and there is no clear separation between the two. I mean, the single particle excitations, they go over into collective excitations in a particular way. Okay, so let me continue here. So a bit of nomenclature. So valence nucleons are the neutrons and protons that are in excess of the last completely filled shell. Okay, and so typically what you will do is that you will not consider the residual interaction between all the nucleons. You can do this, but that's hard, so that's called no-core shell model. But typically what you will do, certainly if you're dealing with a heavy nucleus, you will consider the residual interaction only between the valence nucleons. And then sometimes this is no good at all, and so you should include core excitation. So you should not do this approximation of a completely inert core, but you should allow for some core excitations, and these are usually called intruded states. So that's a bit of nomenclature. So how to derive the residual interaction? Well, the residual interaction, so you can do it microscopically. That's very difficult. As I said, so it depends on the nuclear medium. You have a nuclear mean field potential, so you need to take that into account. So you cannot just put in the free nuclear-nuclear interaction. That's no good. You should renormalize for the effects of the medium. So that's a difficult procedure, which I will not go into. Empirical, this has been done, right? You see, your residual interaction, it's completely specified by a number of matrix elements. So if you know these matrix elements, so these are basically matrix elements of your potential, of your interaction, calculated in oscillator wave functions. So if you specify those matrix elements, then the whole problem is well defined. And so this procedure has been done for the P shell, for the SD shell, and the PF shell. So for the SD shell, for instance, I remembered that there are 63 matrix elements. And so these 63 matrix elements, they've been fitted to the data in order to obtain the best possible interaction. The same thing has been done for the PF shell. There is something like microscopic empirical, so you try to deduce the effective interaction microscopically, but then you find that there are certain deficiencies in this interaction which have to be corrected. And in particular, the monopole part of your interaction should be corrected. So that's what I would call microscopic empirical. And then the most basic approach is to take a schematic interaction. So you assume some simple spatial form, the interaction between the nucleons, and then you calculate the matrix elements in the oscillator basis for instance, the delta interaction. That's what I will show here. You see, this is an example, scandium-42. This is the spectrum of scandium-42. Now, scandium-42, if you look at this diagram here, right? So it has 21 neutrons and 21 protons, and so you can approximate it as a nucleus with an inert core of calcium-40, and then 1 neutron and 1 proton in the F7. So that's the spectrum that you see, and you can link it rather nicely with the residual interaction that you would take for this nucleus. So you see here, the red, they correspond to the t equals 0, and the blue, they correspond to the t equals 1. So the t equals 1, that means that, so these are, if you look at calcium-42 or titanium-42, you would have a spectrum with 0 plus 2 plus 4 plus 6 plus, but these red levels will not appear if you have identical neutrons. So if you have a neutron and a proton, then we have both t equals 0 and t equals 1. And so this is then the interaction that you would choose to do your calculations with. This is the same thing. Yes, this is the comparison with the delta interaction. So you see, this is not so bad. So this is the same empirical matrix elements that we take from scandium-42. These are the matrix elements that you obtain with the delta interaction. There are some problems, right? For instance, the t equals 0, they're much more attractive in the data than they are for the delta interaction. But it's sort of a reasonable approximation to the observed interaction. These are some other, so this is between 0 and 9.5, right? So if I go back to my, so the 0 and 9.5 is here, right? So this will be the shell which goes from n and z equals 40 to n and z equals 50. And so these nuclei are well studied. And so you have here the black dots is an interaction which is derives from niobium 90. So this is one particle in G9.5 and one hole in G9.5. You can then do a Pandia transformation, which all of you should know. And this will give you the interaction for the particle-particle interaction. And then you see SLGT0, that's an empirical interaction that has been fitted to the data. And then the surface delta interaction again, which is not so bad. This is another example. This is even a higher nucleus bismuth 210. So which is one nucleon, 1 neutron and 1 proton above lead-2A. Okay, I would like to finish because I'm over time already. So just to give you an idea of my personal interest in the shell model. So as I stressed several times, shell model, that's it's a heavy numerical procedure, but so typically calculations are done numerically, but what one should recognize is that there are sort of analytical solutions to the shell model, and there are 3 of them. One of them I already discussed, but this is a bit trivial. Namely, if you completely neglect the residual interaction, then you have the independent particle shell model. And that, as I showed, you can solve at least if you take a harmonic oscillator. But even if you take a residual interaction, you still can solve your problem analytically in closed form, so you don't have to do a numerical calculation. You can do it by symmetry arguments, right? And there are two important classes. One class has to do with the pairing interaction, and that is due to Raka, and one is to do with quadrupole interaction. So what I mean is that instead of taking the most general residual interaction, you take a pairing interaction. Or instead of taking the residual interaction most general, you take a quadrupole interaction. In those two cases, they have been dealt with analytically. Just to show you, right? Assume a pairing interaction in a single J shell, right? So this lead to 10. This is, well, I didn't show lead to 10, but I showed something similar for scandium 42 and calcium 42. Okay, so that's the experiment. That's what you get from a delta interaction. A pairing interaction will be degenerate in all levels except the 0 plus. So what you say is actually the two nucleons will interact with each other only when they are coupled to 0. And if you make this assumption, which is a very strong assumption, of course, then you can solve your many-body problem analytically. And this is the solution of your problem. If you put n particles in a J shell with a pairing interaction, you have a closed form for the energy. You can write down the wave functions and so on. And so what you also do, you introduce a new quantum number, and this quantum number is called seniority. And that is the number of nucleons not in pairs coupled to J equals 0, right? And this was due to Raka very long time ago in the 1940s. It has to do with BCS, a correlated ground state solution. It's not a pure single particle excitation, but now you have a correlation, but a correlation of the neutrons among themselves or of the protons among themselves. Okay, I will not discuss that. And then the other, that's I will finish here. So the other analytic solution of your shell model is the SU3 model by Elliott, right, which was also very old. So here what you take is a harmonic oscillator. You cannot put in a spin orbit because that is, then you don't have your analytical solution anymore. And then you take a quadrupole interaction. So where Q is basically R2 R squared Y2. Okay. And if you take this Hamiltonian, again, you have an analytic solution. And what is very nice in this Elliott model is that you see in the shell model, which is a single particle model, right? You see the emergence of collective features of rotational bands. So that's an important feature of this model. And so there are then, of course, many extensions of these two basic ideas. And that's it's a very nice game in order to find sort of intuitively nice and simple approximations to the very complicated many-body problem that is done by the shell. So I will conclude here. So shell model has three phases. So I mainly discussed here the shell structure and the mean field. Okay. Then you can go to pairing interaction. So where you introduce correlations between either only neutrons or only protons. That's the basic pairing interaction that one can consider, right? And then you can go to open shell systems where you have deformation, and there a shell model picture emerges in terms of the SU3 model. So, and I think I will stop here and thank you for your attention. So if there are any questions, I will be happy to try to answer those.
Thank you very much, sir, for the wonderful talk. Now we are going to open this talk for discussion. Anyone, if anyone have any question, he or she can ask.
Yes, I see questions that are asked in the chat.
Yes, sir. We have some.
Should I answer those questions or wait for the person to? Okay, then I will. So one question is, so how does the single particle energy depend on nuclear number? And that's, yes. So how to answer that? So the procedure is the following, that of course you have your if you want to do a shell model calculation, what you should do is to define a valence space, okay, where you are going to put your particles. And then in this valence space, you need an interaction, which I discussed also. You also need some single particle energies. These single particle energies, you should think of them as the interaction of your nucleons in the valence space with your core, right? And these single particle energies, they are defined once and for all for your shell model calculation. So they do not depend on the number of particles, except for possibly, but most people don't do this, a weak number dependence, like a to the mass 1/3 or something, right? To the power 1/3. That you can put in, but it's a very weak dependence on particle number. However, that is not the full story. People talk a lot about effective single particle energies. That's a different matter. Then you sort of, if your number of particles increases in your valence shell, you can you do not change the single particle energies, but you calculate effective single particle energies, which takes into account your the effect of the interactions. Okay. Now this is not needed computationally. Computationally, you don't need effective single particle energies. However, this is a very useful procedure in order to get some intuitive insight into your shell model calculation. And so that is the importance of effective single particle energies. Okay, I think the question was related to that. But if you do a shell model calculation, you're not going to change your single particle energies from one nucleus to the other nucleus by changing the number of nucleons in your valence space. That is not the usual procedure.
Thank you, sir. Thank you, sir. Is there any other question?
Yeah, I see. What is the physical significance of the L² term, orbit term, in the Poorman-Sartre-Fock? Yes, this actually, I had to go very quickly over that, so let me go back. Can you see this? Yes. Okay, so here it is. You see this L² term. What happens? This is an example. Again, it's taken from the book by Bohr and Mottelson, no? So which is the sort of the Bible of nuclear structure physics. And you see, okay, one curve here. Can you see my pointer? Well,
Yes, sir. Yes, sir.
Yes,
It is visible.
you can see the point. Okay. So one curve here is the harmonic oscillator, right? The harmonic oscillator, which is your approximated mean field potential. A better potential would be this Wood-Saxon, which is indicated here with the index S, right? And you see it deviates from the harmonic oscillator, right? So now you take a wave function, and this is a particular example. So you're in the SDG shell, so that means n equals 4 of your harmonic oscillator. And then you look at an S level, S equals 0, right? This is the S level. And you see, well, it sort of wiggles all over, and so the effect of the energy is sort of is averaged out, right? Because the difference between the harmonic oscillator and the Wood-Saxon is that certain regions, the harmonic oscillator is more attractive, right? For instance, here at the interior, certain regions, the Wood-Saxon is more attractive. But for this level here, it doesn't really matter. Okay. However, it matters for a G. So this is an S level. It matters for a G level, right? So this is L equals 4, because this is peaked here. And if you see the difference between Wood-Saxon and harmonic oscillator is particularly important here. And the Wood-Saxon is more attractive. And in order to correct that, you have this L squared term, because the L squared term will put the orbitals with high L at lower energy. And that is what you want, because you're in your harmonic oscillator, you make a mistake, right? Because your potential should be more attractive at the surface. And in order to correct for that mistake, you introduce this L squared term. So that is, it's a very sort of phenomenological way in order to deal with the fact that you're not having the best mean field potential available. I hope that answers the question. Any other questions?
Yeah. Who want to ask their question? So first question is by monthly score.
Excuse me?
We have some offline participants who want to ask their question.
Okay.
Yes, sir.
Hello, sir. Sir,
Yes.
firstly, I would like to thank you for the wonderful talk. I have two questions. My first question is, could you please throw some light on the most suitable nuclear mean field potential to explain single particle properties of nuclei?
So the question, can you repeat it?
Yes, sir. Could you please throw some light on the most suitable nuclear mean field potential to explain single particle properties of nuclei?
Oh, yeah. So that is the most suitable would be this artifact approximation. So that is the best thing you can do, choosing the best V possible. It's still independent particles. Well, you can go beyond that approximation, but okay, that's I would. But the pure Hartree-Fock approximation, so the best mean field, is this procedure. And so it's a bit of a tricky equation. So maybe I should spend some time trying to explain that. So the H here, this H is the total Hamiltonian. So this total Hamiltonian with the kinetic and the residual interaction. So eventually also with three-body interactions, right? So this H is the complete Hamiltonian. The approximation is the fact that you do not take the true wave function of your nucleus, you take a Slater determinant. Right? So, and the Slater determinant tells you that this is still an independent particle approximation. And so you're going to vary your potential, so your mean field potential, in such a way that this quantity becomes minimal. So you minimize the expectation value of your H. And so that is a general principle. I mean, if you minimize that, you have the best available wave function within that approximation of a Slater determinant. Does that answer the question?
Yes.
Thank you, sir. And my next question is that I have heard the term asymptotic quantum number. How is it different from quantum number? Basically, what is the difference between quantum number and asymptotic quantum number?
Yes, asymptotic quantum number is, yeah, this is in the Nielsen model, which unfortunately, the Nielsen model is a very ingenious model in the sense that it's like shell model, but you do not assume that it is a spherical shell model. It's a deformed shell model. Okay, and then you can characterize your single particle states by quantum numbers, and the asymptotic quantum numbers. That is, if you go to the limit of very large deformation, then you recover asymptotic quantum numbers. They're not exact quantum numbers. They're something that appears in a large deformation limit. So it is confined to the Nielsen model, at least in nuclear physics. I don't see any other occurrence of asymptotic quantum numbers than in the Nielsen model. Here I talked about quantum numbers. So all these, so angular momentum is a quantum number, total angular momentum, orbital angular momentum. Eventually the spins can be coupled. These are all exact quantum, well, exact, I mean, they can be mixed, but the angular momentum, that's an exact quantum number. Isospin is a very good approximate quantum number, but not exact.
Thank you, sir. Any other question? Yes, one more participant have his question. On karo mic.
Thank you, sir, for your talk. I want to ask you that what is the difference between spin-orbit interaction in atomic and nuclear physics?
The difference. So in atomic physics, the spin-orbit interaction is weak. And so that means that you're, unfortunately, I don't have a blackboard, so I would like to explain it on a blackboard or a whiteboard, but I can't. So what does that mean? You see, in atomic physics, people talk usually about LS coupling, or the technical term is Russell-Saunders coupling, right? The consequence, that is a consequence of your weak spin-orbit interaction. What does it mean? It means that, you see, you can classify your states by first coupling the angular momenta, the orbital angular momenta of all the particles. So the orbital angular momenta, let me go back to my, so this was here, right? The orbital, all the particles are characterized by a certain orbital angular momentum, L, okay? And so in LS coupling, you couple the orbital angular momenta of the particles to a total L. And you couple the spins, so all the particles carry spin 1/2, and you can couple that to a total spin S. And so your wave function is characterized by orbital angular momentum L, spin S, and total angular momentum J. And this is not what you do in nuclei. In nuclei, because of the spin-orbit interaction, you couple the L of each particle with its spin. And so you couple L, little l here, orbital angular momentum of one particle, with the spin of the particle to the total angular momentum of one nucleon. And then you couple all the angular momenta of the nuclei, all the J's of the nuclei, to the total angular momentum. So it's a different classification system. It's a very important difference between JJ coupling and LS coupling. And this is due to the spin-orbit interaction, which is absent in atoms, but it's very strong in nuclei. So that's an important feature of nuclear structure.
Thank you, sir.
Thank you very much, sir. There is a question by Arunita.
Yes.
Arunita, you can ask your question.
Yeah. Hello, sir. Thanks for the nice lecture. I just have one small question. That is, I have noticed that there is a change in the ordering of the orbital number as we go up with the nucleonic number. For example, when we reach nucleonic number at 82 or 126, the ordering of the orbitals changes. Like, for example, so sometimes 1g7/2 comes below d5/2 and sometimes up. So I'm a bit confused, like why this happens.
Yes, yeah, that's here. Okay, yes. So this is a schematic picture, no?
Okay.
And so, of course, for instance, here that's one example that I'm rather familiar with. So I have here G7 half and D5 half. And these this might change as a function of which nucleus you want to describe, which region you are in, right? And so one should make a distinction between two features. I mean, at the beginning, I talked about effective single particle energies, right?
Yes.
And that certainly is the case, that if you do a shell model calculation, right, then you change the number of neutrons or the number of protons to calculate different nuclei, then the effective single particle energies, they certainly can change the order. And so there could be a switch between D5 half and G7 half. This has to do, for instance, an important feature is this tensor interaction. So the tensor interaction, it has very nice features in the sense that if you fill orbitals for the neutrons, that will have an effect on the ordering of the proton orbitals and vice versa. And that, so spin orbit partners might be getting closer to each other, or they might be repelled by each other. So that's an effect of this. Usually it is due, I mean, the biggest effect comes from the neutron-proton interaction. So if there is an effect of the number of neutrons on the single particle energies of the protons and vice versa.
Okay. Thank you, sir. And sir, one more question.
Yes.
That is, how can shell model explain nuclear isomerism? I think somebody else also asked some of these questions in the chat box. So that is one question I have, the last one.
Yes. Well, I mean, but nuclear isomers, they can be of different types. Huh? So one isomer which I'm familiar with, one type of isomer is the seniority isomer. That's completely describable within the context of shell model, because it has to do with seniority, and so that's a shell model feature, right? Others are much more difficult. You see, there are also things known like shape isomers.
Mm-hmm.
It's not impossible that you can describe this in the shell model, but you have to be, because then shape isomers, they arise because you have two states in the same nucleus with a different shape. And so that hinders the transition from one level to the other level, okay? It's rather hard to describe this in the shell model. It's not impossible. It usually has to do with this business that I mentioned, these intruder states. And so if you have intruder states, sometimes these intruder states, they will have a different shape, a different deformation from the states that you normally describe in the shell model. So, but this is already an involved calculation, because you need states with different shapes in your shell model calculation. Already states the notion of shape is not so trivial in the shell model. So shape isomers, it is possible to describe it in the shell model, but it requires a lot of work. Another type of isomer is K isomers. K has to do with deformation and with rotation. Now there is a description of rotation in the shell model due to SU3, right? So in principle, that's possible, but it becomes very complicated if you go to heavier nuclei, where you have these K isomers, because of the spin-orbit interaction. So that it makes the whole treatment of deformation and rotation features in nuclei much more difficult. So again, that's a difficult thing to describe within the shell model.
Right. Okay. Thank you, sir.
Thank you, sir. Sir, there is one more question by Ritvik. He want to ask that in particle rotor model, we have a term called quasi-particle. So, what does this mean?
So a quasi-particle is actually it's related to a shell model concept. So normally you describe your nucleons as particles, okay? But there is a total equivalent description of the shell model in terms of holes, right? So it's completely equivalent, actually. There is, I mean, you can do it either in particles or in terms of holes. And so you would take a certain valence shell, right, with a dimension, a single particle dimension of, let's say, omega. If you consider the 50 to 82 shell, that will be, you have 32 available single particle levels of single particle states, rather. Okay. So if you're now putting n particles, you can do your shell model calculation. But omega minus n holes will be completely identical calculation. It's formally identical calculation. Now, a quasi-particle, that's a more involved concept, because you do a transformation and you construct creation operators that are a fraction of the creation operator will be a particle, and another fraction will be a hole. So it's a mixture of a particle and a hole excitation. So you break actually a symmetry, you break particle number conservation. But the advantage of breaking a symmetry is that you can introduce more correlations in your system. So you have a sort of a simplified way of introducing correlations in your calculation by doing this. And that is the advantage of these quasi-particles. But then, of course, you end up with states that have not a definite number of particles, which is rather annoying. So you would like to avoid that. So eventually you have to then project on good particle number in order to come back to the true eigenstate with good particle. So quasi-particle, I mean, they arise in many, not only in the particle rotor model, but in many aspects of the nuclear many-body problem.
Thank you, sir. Is there any other question? Sir, we have one more question.
Okay.
We have one more question from Karamjit Kaur.
Hello, sir.
Yes.
Thanks first of all, thanks sir, for your valuable talk. Sir, I have a question that why it is difficult to understand the nature of nuclear forces.
Difficult to understand what?
Nature of nuclear forces.
I didn't catch nuclear.
Nature of nuclear forces.
Why,
Can someone?
sir, she want to ask why it is difficult to understand the nature of nuclear forces.
Oh,
Exact nature.
sorry. Yeah. I'm getting deaf, I think. Anyway, yes, I mean, this I sort of mentioned. You see, if you compare this with the Coulomb interaction between electrons are very simple things. As far as we know, they're point features, so they're elementary. And so the interaction between the electrons is very simple. This is not the case for nucleons. A nucleon exists, I mean, it consists of 3 quarks. And so just describing a nucleon interacting with another nucleon, it's a 6-body problem, right? Because you have 3 quarks here and then 3 quarks in the other nucleon. So, and that is a QCD, which is a very difficult theory. And the other thing I should mention is that QCD is understood more or less for very high energies, but at low energy, this is still a very hard problem to solve. So in any case, you see, they cannot calculate the nucleon interaction in QCD, I mean, at energies that interest us, right? From first principles, they cannot. So they have to introduce some what they call effective field theory. And that basically means that you have a number of coupling parameters that you have to fit to the data in order to describe the nucleon interaction. There is a systematic procedure to doing that, right? But it is complicated. And in addition, because your nucleons are not elementary, that also means that it's not necessarily only 2-body interactions that will contribute. This is one of the main things that has been discovered in nuclear physics, that you need to include, at least in night nuclei, this seems to be obvious, you need to include 3-body forces in order to describe well the binding energies of nuclei. You cannot just have it on the basis of a 2-body interaction. So all this leads to very complicated form of the interaction. That's one of the main reasons why the nuclear many-body problem is so difficult.
Thank you, sir. Sir, we request you the last question of this session by Rajvinder Kaur.
Firstly, thank you, sir, for this talk.
You're
My question, how quantum computing helpful to know about the nuclear properties?
Yeah, I don't know. At the moment, it's sort of very basic. as far, I mean, I'm not an expert, so maybe I'm biased. It's certainly, I mean, quantum computing is interesting from the formal point of view. So, I mean, devising algorithms to solve many body problems. That's certainly it's a worthwhile endeavor to do. But then you have to look at what kind of problems they can actually solve. And these are very, very basic, very simple problems at the moment. And so I don't know enough about technology. So whether they really can push the technique of quantum computing, there are things like what is it, noise. I mean, you have to be aware of the noise and be able to take care of that. So these are all technological things that maybe will be solved, maybe not, I don't know. Right? But at the moment, I would say quantum computing is not going to, it is not adding anything to the solution of the many, at the moment, let's say at the moment, of the nuclear many body problem.
Okay, sir. Thank you.
Thank you very much, sir. Hope we have answered all the questions. Now this session is closed for discussion and it is open for vote of thanks. Dr. Amandeep Kaur.
On behalf of Department of Physics, Akal University, I am thankful to our Honorable Vice Chancellor for encouraging us and granting approval for organizing this webinar at university. I would like to express my sincere appreciation to Registrar Akal University for his invaluable support in making all the necessary arrangements for the webinar. A very special thank you to Professor Isacker for sparing your valuable time to share your insights and knowledge with us during this webinar. Sir, your presence has enriched our learning experience immensely. Thank you so much. I'm also grateful to all the faculty members of the Department of Physics for support and cooperation throughout the planning and execution of this event. A big thanks to Ms. Manpreet Kaur, research scholar from Department of Physics, for her efforts in organizing this lecture. I extend my appreciation to the IT staff of Akal University for their technical support and assistance in ensuring a seamless virtual experience for all the participants. I am thankful to all the participants from various institutes across the globe. Finally, in the end, again, I would like to thank you, Professor Isacker, and we hope to have a privilege of hosting another session with you, sir, in future. With these words, I hereby conclude this vote of thanks. Thank you all again for your unwavering support and participation. Thank you so much.
Thank you.
Thank
So
you,
I'm very happy I did this. This was a nice chat with my Indian friends. I like very much. I mean, it's a pity that it has to be done by remote, but it was very nice anyway. So thank you for the invitation.